Hello guys, welcome to my channel Maths 4747. I am going to solve some more examples of matrix spaces. In previous video, I have given only one example with x is equal to r. Now here I am just going to prove some more matrix spaces. So if we take x as Rn and your dxy is given as summation I from 1 to n this xi minus yi square and whole to the power 1 by 2. This is the matrix defined. Now we have to prove is this R and D is a matrix space or not. So we have to prove that this R and D is a matrix space. So in order to prove this as a matrix space, what we have to do? We have to prove all the four properties. Now first one is dxy greater than equal to 0. Second property is dxy is equal to 0 if and only if x is your y. And third one, symmetric one, that is dxy is equal to d of yx. And the fourth one, triangle inequality, that is dxy is always less than equal to d of xz plus d of zy, where these x, y and z belongs to what? Rn. Now guys, what is Rn? Let's first I introduce what is Rn. So if we take n as 2 or you can write n as 3. So this is your real line, like minus infinity to infinity, and in two dimensions like this, x-axis and this is your y-axis. So this is your R2 plane. There are two axes. If we have three dimension, like three axis, x-axis, y-axis, and this is your third axis. So this is your R3. So and so on, we can get Rn. But in daily life, you have shown only this R2 plane and that R3. Normally, this is your space R3, in which three dimensions are there, x, y, z. So in R2 plane, any point on this plane is of type xy, or you can write some AB, where A is from x and B from y. And in R2, there is any point of type x, y, z, or like A, B and C. So there are three length vectors, A from x, B from y and C from z. Like this, in Rn, any element of Rn is of type x1, x2 and so on. This is the single element of Rn. Like we can write x belongs to Rn. It means x is x1, x2 and xn. And if y belongs to Rn, it means y is y1, y2 and so on yn. So in this case, we can write all the elements of Rn. So what we have to prove? We have to prove R and D is a matrix space or not. So we have to pick some elements from Rn. So if x and y belongs to Rn, then your x is of type x1, x2 and so on xn. As I discussed before, y1, y2 up to yn. There are two elements from Rn. So my first point is what we have to show. We have to show dxy is positive, greater than equal to 0. So by using definition, your definition is of this form: I from 1 to n xi minus yi square and whole to the power half. So as you know that these are the entries of x, x1, x2 and so on up to n, the summation. So what we can write? We can expand summation. So this is x1 minus y1 square plus x2 minus y2 square and so on. This is xn minus yn square and whole to the power half. You know that these xi's, x1, x2, xn, these belongs to R. These are real numbers. If we subtract x1, y1 from x1 and this whole square, this is a positive quantity. This one is also positive. This one is also positive. The sum of positive quantities is always greater than equal to 0. Right? So this dxy is greater than equal to 0. That means first property is verified because sum of square terms is always positive. So now second one. Second, what we have to do? We have to prove dxy is 0 if and only if x is equal to y. Now what is your dxy? First of all, write down the definition. Thus xi minus yi square and whole to the power half. This is equal to 0. We can square both sides. We get thus summation I from 1 to n xi minus yi square, that is equal to 0. Now we can open this summation. Now this x1 minus y1 square, x2 minus y2 square and so on, xn minus yn square, that is equal to 0. As I discussed earlier, this is positive quantity, this is positive, and sum of these positive quantities is equal to 0. This is possible if and only if this xi is equal to yi for every I. I varies from 1 to n, right? So if all the xi's are equal to yi's, it means x is equal to y. So if dxy is 0, then we have proven that x is equal to y, and this is the if and only if part. If we take this x is equal to y, then dxy is 0. So now third property, the symmetric one. Third, your dxy is equal to dydx. This thing we have to prove. So take left hand side, dxy, that is equal to from I from 1 to n xi minus yi square, and this is this one. Now we can write this quantity as yi minus xi because this is square. So we can write this. These two are same. Now this thing is what? This is d of yx. Now symmetric property is also verified. Now guys, last one, that is important one, that is dxy is less than equal to dxz plus dzy. This thing we have to show. So we have taken again left hand side, that is dxy. So I from 1 to n, and this is xi minus yi square and whole to the power half. So what we can do, I from 1 to n. So we have added dz zi and minus zi. So this is this one. Now we can separate these two as I from 1 to n. This is xi minus zi plus zi minus yi, and this is whole square, whole to the power half. So guys, now we have to open this square, and this is equal to summation I from 1 to n. This is what? xi minus zi square plus zi minus yi square and plus twice of xi minus zi and zi minus yi, this one, and whole to the power half. Now we can operate summation individually, and this is xi minus zi square plus summation I from 1 to n zi minus yi square, and this is twice summation I from 1 to n. This is xi minus zi and zi minus yi, and whole to the power half. Now we have used here Cauchy squares inequality in order to simplify this. So what is that Cauchy squares inequality? This is standard inequality. So the inequality is summation ai bi I from 1 to n, this is less than equal to summation ai square I from 1 to n and summation I from 1 to n bi square, and this to the power half and this to the power half. So this is Cauchy-Schwarz inequality where ai is bi, this belongs to r. So this is your Cauchy-Schwarz inequality, so we have to use that. Xi minus zi, this is also a real number and this is also a real number, so we can apply this Cauchy-Schwarz inequality. What we get, just replace this. So this is less than equal to, from here connected, less than equal to summation I from 1 to n xi minus zi square plus, first two terms are same, so zi minus yi square, and this twice, this is less than equal to I from 1 to n, in place of ai there is xi minus zi, this square and to the power half, and second term is summation I from 1 to n zi minus yi, zi minus yi square and whole to the power half, and there is a whole power also, that is 1 by 2. So what is this? This is a perfect square of what? This one, this term, these two terms. Okay, so what we can write? Summation I from 1 to n xi minus zi square, and there is a half plus summation I from 1 to n zi minus yi square half, this square, this is half, and there is a whole power 1 by 2. These two are cancelled out, and this term, this is equal to, this is what? The first term. This is d of xz plus this is d of zy. So what we get? dxy is less than equal to d of xz and d of zy. So my last property is also verified. That means R and D is a matrix space with the given matrix. D is a matrix space. So you can prove this type of examples, like if we have n is equal to 2, n is equal to 3 and so on. So we can prove these type of examples by using this way only. So this is the easiest approach solving. R and D is a matrix space.